Welcome to the next lecture of the matrices. In today's lesson, we will talk about types of the matrices. In the previous lesson, we had already seen what is a matrix, what is the order of the matrix, and how elements of the matrices are represented. So let's see what types of the matrices in this lesson we will discuss. So we will discuss about row matrix, column matrix, null matrix, square, diagonal, scalar matrix, unit matrix, transpose, symmetric, skew symmetric, upper triangular, lower triangular matrices. There are lots more matrices, and we will discuss those matrices. Let's say orthogonal matrix, and there are more matrices we will discuss into the next lesson. So let's start discussing this. One is the row matrix. We had already discussed these two, row and column matrix, in the previous lesson. Let me give you a very quick view of these two types of matrices. First is the row matrix. So a matrix with a single row and many columns is known as a row matrix. So this is the example. You can see in this matrix we have only one row and we have more than one columns. We can have one or more than columns. So this kind of matrix is called as a row matrix with one row and more than one columns. So this is a row matrix. So what is the next? The next is the column matrix. So now let me talk about the column matrix. Wherever we have one column and we can have as many as rows. So you can see this is a matrix with one column only. So this is with one column and three rows. We have three rows, 1, 2 and 3. We have three rows, but we have only one column. So this type of matrix is known as a column matrix. As I have already told you that this 1, 2, 3, 4, this matrix, this is having two rows, 1 and 2, and this is also having two columns, one column and two columns. So this is having two rows. This is one row and this is second row, and this is having two columns, column 1 and this is column number 2. This matrix is neither a row matrix nor a column matrix, but this is a column matrix. And previously we had studied 1, 2 and 3. This is a row matrix. So now let me erase this and let's move further. Let's discuss this next category. This is null or zero matrix. Any matrix with any number of columns or any number of rows with all the elements as zeros. Yes, if we have all the elements in any matrix where all elements are zero. We can see this is a matrix with two rows. So we can see we have two rows here. This is row number 1 and this is row number 2, and this matrix is also with two columns, column number 1 and this is column number 2, but all the elements into this matrix are 0. So this type of matrix is called as a null matrix or a zero matrix. So let me write this. This is a what is this? This is a column matrix, as we have single column, as well as this is a null matrix, or we can also call it as a zero matrix. Let me write one more example. Let's say this is, so this is, we have a row matrix with all elements as zeros. So this is a null matrix as well as zero matrix. Now let's discuss the next type of the matrix, that is the square matrix. So next we have a square matrix. So a matrix where number of rows and columns are equal, that will be called as a square matrix. Yes, so if we have a matrix, let's say if this is a matrix, yes, this is also a matrix because it is having single row and single column. So we can see the order of this matrix is 1 cross 1, where number of rows and number of columns are equal. So this is a square matrix. Next is, let's say if we have 1, 2, 3, 4. In this matrix, we have two rows, 1 and 2, and in this matrix, we have two columns as well, 1 and 2. So the order of this matrix is 2 cross 2. So this is also a square matrix where number of rows is equal to the number of columns. This is called as a square matrix. Let me write one more example. If 1, 2, 3, 4, 5, 6, 0, 3 and 2. So here we have 3 rows in this matrix, row number 1, row number 2 and row number 3, and we have 3 columns in this, column number 1, column number 2 and column number 3. So the order of this matrix is 3 cross 3. Again, this is a square matrix where number of rows is equal to the number of columns. So this is the square matrix. Now let's talk about the next definition, the next type of the matrix, that is called as a diagonal matrix. So what is a diagonal matrix? The first condition of the diagonal matrix is it has to be a square matrix. So this is the first condition for a matrix to be a diagonal matrix, that it has to be a square matrix. Next, the second condition, all non-diagonal elements must be 0. All non-diagonal elements must be 0. So what are non-diagonal elements? So let me give you an example. Let's say if this is a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. The first condition, we will check whether this is a square matrix. Yes, this is a square matrix because we have equal number of rows and equal number of columns. So we have 3 cross 3, 3 rows and 3 columns. So this is a square matrix. Now what is a diagonal into this? The diagonal is the elements which have same number of row and same number of column. So this is row number 1, row number 2 and row number 3. This is column number 1, column number 2 and column number 3. So we will find out the elements with same row and same column. So we can see this is 1 with first row, first column. This is second row, second column, and this is third row and third column. This is called the diagonal of the matrix. So this is these are all the diagonal elements into this. So these are all the diagonal elements. So what is the second condition? That all non-diagonal elements must be 0. That means this should be 0, 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 as well as this should be 0. So this will be a diagonal matrix. So because this matrix is following both the two conditions, it's a square matrix and all non-diagonal elements are 0. Let me show you one more example. So this is, let's say 1, 2, 3, 4, 0, 0, 0, 0, 0, 0, and okay. So this is another example. Let's verify both the conditions. It's a square matrix, yes, because it has 4 rows as well as 4 columns, and all the non-diagonal elements here are 0. So this is a diagonal matrix. Let's move on to the next definition. The next definition is a scalar matrix. Basically, scalar matrix is a special case of the diagonal matrix. So it's a special case of the diagonal matrix. Let's write down the conditions for a matrix to be a scalar matrix. We have already done diagonal matrix. Now we are talking about scalar matrix. So which matrix will be a scalar matrix? Condition number 1, it has to be a square matrix. Condition number 2, it has to be a diagonal matrix. And condition number 3, all elements of diagonal must be equal. Then this will be called as a scalar matrix. So we have 3 conditions. 1, the matrix has to be a square matrix. It has to be a diagonal matrix. That means all non-diagonal elements must be 0. And third, all elements of the diagonal must be equal to these must be equal to each other, right? So these must be equal to each other. Okay, so let me show you one example. Let's say if we have a matrix 2, 2 and 2, 0, 0, 0, 0, 0 and 0. So let's verify all the 3 conditions on this matrix. Whether this is a square matrix, yes, 3 rows and 3 columns. The order is 3 by 3. It's a square matrix. Second, whether it's a diagonal matrix, all non-diagonal elements, so this is a diagonal, all non-diagonal elements 0 are 0. So you can see all non-diagonal elements, these all three elements and these all three elements are 0. So this is a diagonal matrix. And the third condition, all elements of diagonal must be equal. So we can see in the diagonal we have all 2's, all three elements are equal. So this type of matrix will be a scalar matrix. Let me show you one more example of a scalar matrix. Let's say if we have a 4 by 4 matrix with the diagonal elements are all equal to 4. So what about this matrix? What about this matrix? This matrix is a square matrix, as it's a 4 by 4. This is a diagonal matrix because all non-diagonal elements are zeros. All non-diagonal elements are zeros and all diagonal elements are equal to each other. So this is a scalar matrix. So let's move to the next definition, that is the unity or identity matrix. So next is unit or identity matrix. So this is another special case of the scalar matrix. So any scalar matrix where all diagonal elements are unit, that means all diagonal elements are 1. So if we have all diagonal elements are equal to 1, that will be a unit matrix. Let me show you an example. So if we have this matrix with diagonal elements all 1 and non-diagonal elements are all 0. So let's verify all the conditions. Do you know this is a scalar matrix? Yes, this is a scalar matrix because it's a square matrix. Non-diagonal elements are all 0 and diagonal elements are all equal, and on which we are applying a special condition that all diagonal elements are 1. So we can see these are all the diagonal elements. Now let's verify all the three conditions. It's a square matrix. Yes, it's a square matrix. 3 by 3, 3 rows, row number 1, 2, 3, column number 1, 2 and 3. 3 rows and 3 columns. It's a diagonal matrix. Yes, all non-diagonal elements are 0. And the third condition, all diagonal elements are equal to 1. So we can see all diagonal elements are equal to 1. So this is called as a unit or identity matrix. Now let's talk about the transpose of a matrix. What we mean by the transpose of a matrix. Let's say if we have a matrix A with elements 1, 2, 3, 4, 5, 6, 7, 8, 9. Then how we can obtain the transpose of the matrix? The transpose will be represented by AT, and we can obtain the transpose of a matrix by interchanging rows with columns, right? So let me show you. Then the transpose of this matrix A will be, let me interchange the row with column. So this is the first row, 1, 2 and 3, and I am going to convert this into the first column here. So I'll write 1, 2, 3. So now this is the second row, 4, 5 and 6, and I will convert this into the second column. This will be 4, 5 and 6. And this is the third row, 7, 8, 9, and will be converted to the third column, that is 7, 8, 9. So now this obtained matrix will be termed as the transpose matrix of the given matrix. So this is how we can obtain the transpose of a matrix. So I hope you have understood the transpose. Let me show you one more example. Let me clear it with one more example. The transpose of a matrix. Let's say if we have a matrix 1, 2, 3, 4, 5, 6. And what will be the transpose? Let's say if we call it as A, then A transpose will be equal to, we need to convert rows into columns. So this is the first row, 1 and 2. So I'll convert this into first column, 1 and 2. This is the second row, 3 and 4 will be converted into second column, 3 and 4. This is the third row, 5 and 6 will be converted into the third column, 5 and 6. So this is the transpose of the given matrix A, right? So now let me discuss the next definition. That is the symmetric matrix. When a matrix will be a symmetric matrix, it's pretty simple. If the matrix A is equal to its transpose, then it will be a symmetric matrix. So let me show you an example. If we have 1, 2, 3, 2, 4, 5, 3, 5, 6. Let's say if this is a matrix A. Now let's identify what will be its transpose. So let me write its transpose. Let's say we call it AT. So its transpose will be obtained by interchanging rows and columns. So this is the first row, 1, 2 and 3, and let me write it as first column 1, 2 and 3. This is the second row, 2, 4 and 5. Let me write it as a column 2, 4 and 5. And this is the third row, 3, 5 and 6. Let me write it as a third column 3, 5 and 6. Now we can see whether this and this are similar. Right, both these matrices are similar matrices. So we can see that the transpose of this matrix is equal to the matrix, and hence this matrix A is a symmetric matrix. There is one more condition for the symmetric matrix, that for every element Aij, it should be equal to Aj. Right, let me show you how. Ai, where I is the number of row and j is the number of column. So let's say if A12 should be equal to A21. Let's verify. What is A12? First row, second column. This is 2. And what is 21? Second row, first column. This is 2. Both are equal. So we can see these two elements are equal. Then let me check again. A31 should be equal to A13. What is A31? This is A31. A31. This is third row and first. This is A31. And what is A13? First row and third column. This is 1, 3. You can see 3 and 3 are equal to each other. Let's check once more. A23 and A32. What is A23? This is second row, third column. That's 5. Should be equal to A32. That's third row, second column. This is 5. And we can see all the elements are equal. So we can see opposite to the diagonal elements must be equal. 2 and 2, 3 and 3, 5 and 5. So this is how we can see that a matrix will be a symmetric matrix. To be very simple, if the matrix is equal to its transpose matrix, then this will be called as a symmetric matrix. Right. Now let's move to the next, that is the skew symmetric matrix. So what will be a skew symmetric matrix? It's again a simple thing. If a matrix is equal to its negative transpose, then this will be a skew symmetric matrix. So now let's see what will be a skew symmetric matrix. If this is 1, 2, 3, let's say -2, 4, 4, -3, 5, let's say this is -4 and 6. And this is a matrix A. What will be its transpose? Let's convert this into its transpose. So row will be converted to column. This is 1, 2, 3, -2, 4 and 4, -2, 4 and 4, -3, -4 and 6, -3, -4 and 6. Now we can see that this is its transpose, but it's the negative transpose. So we can see the elements are different. It's -2, -3, and here it's -2, it's 2, 4, 4, -4. Or we can also say in the other terms that if for all Aij it is equal to minus of Aj. Right, all Aij should be equal to minus of Aj. Let's say if it is A12, then it should be equal to minus of A21. What is A12 in this case? A12 is 2. So we can see that this is 2. Should be equal to minus of A21. What is A21? This is -2. So minus of -2 comes to be 2. Right. So let's check once more. A23 should be equal to minus of A32. What is A23? In this case, A23 is this 4. So this is 4. And what is A32? This is third row, second column, -4. So if we'll use minus and -4, so this is minus of -4 is 4. So we can see A23 is equal to its minus of A32. So this will be a skew symmetric matrix. So I hope you have understood the concept of the skew symmetric matrix. Let's move on and talk about the next two types of the matrices, that is the upper triangular matrix and the lower triangular matrix. So we have two conditions in upper triangular matrix, that it has to be a square matrix, and in the second, all elements below diagonal must be 0. All elements below diagonal must be 0. For example, if we have 1, 2, 3, 4, 5, 6, and these are all 0 below diagonal. So this is a diagonal, and all elements below diagonal must be 0. This is called as an upper triangular matrix, right? Let me give you one more example. Let's say if we have a square matrix, right? So this is also a square matrix, and this is the diagonal, and all elements below diagonal are 0. So this is the upper triangular matrix. Opposite to this, we have lower triangular matrix. Lower triangular matrix with one change: all elements above diagonal, must be 0. So what will be the example? Let's say 1, 2, 3, 4, 5, 6, 0, 0 and 0. So you can see this is the diagonal, and all elements above diagonal are 0. This is the lower triangular matrix. Another example, let's say if we have 1, 2, 3 and 0. So you can see this is the triangle, and all the elements above diagonal are 0. So here we have this lower triangular matrix. So we have studied all these definitions, all these types of the matrices: row, column, null, square, diagonal, scalar, unit, transpose, symmetric, skew symmetric, upper and lower triangular matrices. I hope you have understood this concept. Feel free to ask your queries using the comment box, and we'll meet in the next lesson with some more types and definitions of the matrices. Thank you so much.